Today, we are looking at functions, and the absolute most important rule to remember is this. If a function is linear, it takes a steady, constant step forward every single time. Looking at this graph mapping the forest, we can see two different paths. The fox walking along the bottom trail moves forward exactly 2 units at a time. That's a steady progression. But the fireflies beside the trail, they burst upward in larger and larger jumps, making a curve. If a mathematical relationship changes by the exact same amount at every interval, like the fox, it quite literally walks a straight line. We call that a linear function. Before we even look at the math or calculate hard numbers, training your eyes to spot that steady, unchanging step is how you distinguish a linear function from a nonlinear one. Let's test this rule with some actual data. Here we have 2 tables charting numbers along a riverbank. Table A and Table B both start at the point 0, 2. But we need to figure out which one is a linear function. To find out, we check the change in the y values. In Table A, moving from 2 to 5 is an addition of 3. From 5 to 8 is another jump of 3. And 8 to 11 is 3 again. Because Table A consistently adds exactly 3 at every single step, its rate of change is constant. That means Table A is linear. Now take a look at Table B. Pause for a second and check the y values. What is the change between those steps? Here, the y values change by adding 2, then adding 4, and then adding 8. Plotted out, that forms a curve, not a line. This is a crucial distinction. Table B has a predictable pattern, the numbers double, but it is only linear if the additive change stays perfectly constant. We can also spot this constant change straight from an algebra equation. Let's look at this grid mapped on the tree trunk. What do the numbers in the equation y equals 4x plus 7 tell us about the shape of the graph? The constant number 7 at the end tells us our initial value. This is the y-intercept, which means our graph crosses the vertical axis exactly at 7. The number 4 attached to the x is our coefficient. It tells us the rate of change, or the slope. For every 1 unit the graph moves to the right, it rises exactly 4 units up. Because this equation has the form y equals mx plus b, it defines a linear function. Memorizing y equals mx plus b gives you a structural map. It guarantees a starting position and a reliable, steady step for the relationship. We can use these same checks in real-world contexts too. Look at this scenario. A local gym charges a $15 sign-up fee, plus an additional $8 for every visit. Is the total cost a linear function of the number of visits? We start by identifying our initial value. That $15 sign-up fee acts as our starting point, our y-intercept. Then, every single time you visit the gym, the cost increases by the exact same amount, $8. That represents our steady steps forward. Because the output changes by the same $8 for every single visit, this real-world scenario perfectly models a linear function. Linearity always comes down to structure. Whether we are calculating the constant additive change between points in a table or identifying the slope and intercept in an equation, we are looking for that same unchanging, steady progression. Recognizing this boundary between linear and nonlinear patterns helps us choose the right mathematical tool for the job. Once you confirm a rate of change is constant, you can use the structure of a linear function to predict exactly where the next step will land. As you look at the patterns around you, ask yourself, is the rate of change constant here?